Hello everyone. Let's review this paper. So, as we know, vision language models are powerful because they can process both visual and textual data simultaneously, enabling applications like image captioning and VQA, etc. However, traditional methods typically encode images and videos into separate feature spaces, leading to misalignment before projection. This separation makes it difficult for the large language models to effectively interact across modalities. So to tackle this one, this paper proposes a unifying visual representation into the language feature space, creating the language and the visual learning model. The resulting model is named as titled as a video lava, which is a robust baseline that allows images and videos to mutually enhance each other. So I'll be focusing on the key advancements in the vision language models, focusing on the video lava framework. So we will start with introduction to recent works that set the stage for our research. Then I will highlight the unique contribution of video lava, how it compares to other models. Next, we will explore the video lava architecture and its capabilities in processing images and videos. I will then explain the training setup, including the datasets and the techniques used. Further, we will also cover some ablation studies to understand the impact of different components on overall performance. Finally, I will summarize the key takeaways and discuss future research directions for enhancing the model. So I'm excited to share these insights. Let's dive in. So the landscape of large vision language models primarily features models designed for either image language or video language tasks, limiting their versatility across visual modalities. So models like video chat and video llama aim to bridge this gap by using shared visual encoder for both images and videos. However, since images and videos are fundamentally different, these models struggle to create a cohesive representation, resulting in a significant performance gap compared to specialized video models like Video ChatGPT, which excels in video-specific tasks. Alternatives like XLLM and Macaw LLM use separate encoders for images and videos, but still fall short of the performance seen in dedicated video models. The core issue lies in the lack of alignment before projection, as image and video features exist in different and distinct spaces, making it difficult for the vision language models to effectively process both modalities. This misalignment prevents them from fully leveraging the strengths of each. So now let's look into the works which are along the lines of video lava or prior to the video lava as well. So the current models often rely on ineffective projection layers, complicating large language models learn interactions between image and video modalities. So this misalignment is a common issue seen in models like Albef Wilt, where proper alignment before fusion is critical for performance, like trying to fit mismatched puzzle pieces. So, for example, there is a method, a work known as ImageBind LLM, which attempts to align multiple modalities into the common feature space by converting them into image features. So, this approach simplifies processing akin to using a universal language for different data forms. It even retrieves similar image features from training-free database, enabling a more unified handling of modalities. However, there is a downside. The indirect alignment method can degrade the performance, and the lack of direct knowledge about the video data limits its effectiveness in certain situations. So, while image-bind LLM is an innovative step forward, there are still challenges to address. So, what is the main contribution of this work? So, the Video Lava innovatively connects visual signals with the language feature space. So, it tries to map a unified visual representations to the language feature space. That is, a key feature of Video Lava is its alignment of visual modalities before projection, enhancing performance significantly. That is, there is an image and there is a video, right? So after passing the respective modalities to their respective encoders, there is an alignment is happening. So before the projection to the LLM space, that's what I was referring to. So this unified framework allows large language models to perform visual reasoning across both images and videos, bridging the gap between these modalities for richer analysis. So the extensive experiments done in this paper demonstrates that this unified representation enables LLMs to process images and videos seamlessly. In fact, Video Lava outperforms models designed solely for images and videos, highlighting the benefits of leveraging both modalities together and paving the way for advanced future applications. So when we are trying to extend, so when we are extending large language models for solving multimodal tasks, right? So it can categorize into two kinds of approaches. So one is scheduler kind of approaches, another is the decoder kind of approach. In scheduler approach, LLM acts as a conductor, orchestrating how different modalities to interact to ensure harmonious integration. When it comes to decoder approach, LLMs functions as a translator, converting information between modalities, such as turning visual data into a descriptive text. So to clarify these approaches, we can refer to this table. So highlighting basically like what are the highlighting the strengths and weaknesses. This visual aid is essential for selecting the right strategy for a specific application. So just in order to give a brief, just like let's dive into the scheduler-based methods. The idea here is a pretty fascinating, right? So we treat various visual models like plug and play modules. So picture it as assembling building blocks where the LLM schedules these modules based on what specific visual task requires. For example, you might be familiar with the Visual Chat GPT and Hugging GPT, right? They primarily focus on images. On the other hand, we have React and Viper GPT, which extend their capabilities to handle videos as well. One of the standout benefits of these scheduler-based large vision language models is that they don't need end-to-end training. This is a game changer because it allows us to bypass the usual pre-alignment and joint training process for each modality. So we can be more efficient while still leveraging the strengths of each module. Next, let's dive into the focus of our discussion today, which is primarily on how large language models or LLMs can be improved as a decoders. See, our goal is to enhance the alignment of these models with the visual data, making them more effective in understanding and interpreting images and videos. Now, if we look at MiniGPT, we see some limitations. It aligns image tokens using a linear projection layers. But This approach isn't particularly robust. It often lacks the strength that comes from incorporating the human feedback, which is essential for nuanced understanding. So in contrast, Impleg All takes more innovative approach. It employs two-stage training process. First, it aligns images with the language. Then it refines this alignment through human instruction datasets. This method is promising because it allows the model to learn from the feedback and enhancing its performance. See, when we talk about scaling with large data sets, models like InstructBlip and Lava really shine. They leverage extensive human instruction data sets, allowing them to train larger LLMs, some reaching up to 13 billion parameters. This scaling is crucial for improving the model's capabilities. Lastly, it's important to note that adherence to instructions is a key part of their training process. These models follow strict guidelines during end-to-end training, which significantly enhances their visual reasoning capabilities. So in summary, by focusing on the strategies, on these kind of strategies, we can make significant strides in aligning LLMs with visual data, ultimately improving their performance and the utility. So now we focus on LMs as a decoders, right? So because as we discussed earlier, LMs as a schedulers, right? So here let's discuss a video ChatGPT, which created a data set of 1 lakh video instructions. So here actually what this slide shows, right? These are the different works that are using LLMs as a decoders when they are trying to extend LLM's capabilities to video. Right? So as part of that thing, the video chat GPT introduced a 1 lakh video instructions, which helps large language models or LLMs better understand the video content. Next, after the video chat GPT, we have video chat and video llama, which achieve multimodal capability through joint training. This allows them to handle both images and videos at the same time. So when we expand LLMs to include new visual modalities, pre-alignment is often necessary. This is evident in models like Llama Adapter and ImageBind LLM. These models connect different modalities to image space using ImageBind's modality encoder, which enhances multimodal reasoning. What sets Video Lava apart is that it is not only pre-aligns the image and video features, but also conducts joint training for a unified visual representation. This significantly boosts its multimodal reasoning capabilities. So far, we have focused on how literature motivated this work. Now we dive into the framework of this paper. Let's start with the overview of the Video Lava framework. This system utilizes language-bind encoders to extract features from the raw visual signals like images and videos. What's really interesting is how it integrates large language models such as Vicuna, which is significantly enhances its processing capabilities. Now, to facilitate this integration, Video Lava includes visual projection layers. These layers, so it's like visual projection layer is nothing but FP here. So image bind, language bind encoders are sitting inside this encoder soup, that is FP. So the Video Lava includes these visual projection layers. These layers transform the visual features to ensure they align well with text data. Speaking of text, there is also a dedicated word embedding layer here, which is denoted as FW in the figure, that embeds the textual data into the system effectively. See, when we talk about feature extraction, it's all about those language-bind encoders again. They are specifically designed for multimodal input, which means they can handle different type of data seamlessly. As a result, these encoders create a unified representation, mapping a various modalities into a single textual feature space. So to maintain consistency in how these representations are processed, Video Lava employs a shared projection layer. So there is a common projection layer FP, right? So once we have the processed visual data, it combines with the tokenized textual queries. This merging is crucial because it sets the stage for the next step, that is the response generation. So finally, all of this combined input is fed into the large language model, which generates coherent responses. The overall objective of the Video Lava is to leverage both visual and textual data, enabling meaningful interactions that can enrich user experience. So now we talk about unified visual representation. So that is, let's dive into this main goal, which is really interesting. See, mapping images and videos into a shared feature space, right? That is a very interesting one. By doing this, we can enable that large language model to learn from the unified visual representation. So that is, rather than having a separate representations for the image and video, there is a common representation for both. So that allows the model. So it's like it is fascinating to think in that same information, right? Like suppose, for example, in the text, if I say running dog, that can be expressed through a different media, whether it is a language, image, or video. But semantically, all those are conveying the same meaning, that is running like a dog. So now, but why this is important? Like by compressing information from these various modalities into a common feature space, we allow the model to extract valuable insights from this dense representation. This approach enhances the interaction between modalities, making them more complementary. So to bring this vision to life, they have decided to use a modality encoders from the language bind. These encoders are effective at aligning images and videos with the textual feature space, helping us achieve that unified representation that we aim for. Overall, this approach opens up a lot of exciting possibilities for understanding and utilizing visual data. Let's discuss that language bind. It's like alignment before projection. See, when it comes to language bind, right, it begins with OpenClip. So what is that OpenClip? It is creating a common feature space for aligning images and language, which is crucial for subsequent steps. That is, next, it incorporates video representations using a vast data set of 3 million video text feeds from Vidal 10, enhancing its capabilities significantly. That is, a key aspect is emergent alignment, where video and image representations integrate seamlessly. Both encoders utilize the language bind encoders too, ensuring pre-alignment inputs for the large language model. This approach effectively minimizes the representation gap between the different visual signals, resulting in a unified representation that feeds into shared projection layer before reaching the LLM. This integration enables more effective interactions between the visual and the language data. Now let's dive into that training process of this Video Lava. It's quite similar how large language models such as GPT series operate. The process kicks off with two main inputs, right? So text input, that is XT, and the visual input is XV. These inputs are then encoded into sequence of tokens. Now the core goal of the model is to maximize the likelihood probability. This is a crucial step because it significantly boosts the model's multimodal understanding capabilities. Essentially, it helps the model better interpret and integrate information from both text and visual sources. See, when we look at the model's architecture, there are a couple of key parameters to consider. One is L, which represents the length of the generated sequence. Length of the generated sequence, that is XA. Another important parameter is the theta, which is a trainable one. This means that it can adapt and improve through training process. What is particularly interesting about Video Lava work is that its approach to training. It doesn't focus on one type of the data. Rather, it conducts joint training on both images and videos. This ensures that each training batch contains samples from both modalities, fostering a more integrated understanding of visual and textual content. This comprehensive approach is what sets Video Lava apart in its multimodal capabilities. See, there are couple of stages involved in training the Video Lava. Let's discuss about the training phases, right? So as part of that one, there is a stage one. They called it understanding training. They called that phase name. Okay. So here basically, this training phase of this model, right, which aims to enable it to interpret visual signals, we utilize a substantial data set of image and video text space. Each visual signal corresponds to a conversation data pair denoted as XQ, XA, where XT equals XQ and XK is the ground truth. This structure is vital for model's learning process. So the primary goal during the training is to minimize the autoregressive loss, which helps the model to develop essential skills in visual comprehension, right? To streamline training, so we have to freeze the certain parameters in the model, allowing us to focus on enhancing the visual representations without interference. This strategy lays the groundwork for building the robust model's capabilities of effective understanding complex visual signals. Similarly, in the second phase of the training is known as the instruction tuning. Okay, so it's not just about describing any visual signals anymore. So that skill has been already learned in the stage one. Now it's about responding to complex instructions that require deeper comprehension. So regarding the conversation data, so we have multiple interaction rounds. So, so here in this phase, what we do is basically when R is greater than when. R is means it's like we concatenate all previous conversations with the current instruction to provide the full context. So although we are in a new phase, the training objective remains the same. So generating the appropriate responses across various instructions. So large language models assist in this learning process. So by the end of both stages, right, understanding stage and instruction tuning stage, what we expect is the model to be more skilled at generating relevant responses based on diverse instructions. So now let's get into experiments. So let's talk about the core components of this model. So they are using Video Lava is using basically Vicuna 7B as a LLM backend. So which is a strong choice for handling a diverse language task. Next, the visual encoders are derived from the language bind. They are initialized using VIT L14 architecture, which helps us effectively process visual data. For text processing, they have integrated text tokenizer from Llama. So, and finally, they also used shared projection layer, which consists of two fully connected layers. These layers play a crucial role in merging the visual and textual data, so enhancing the model's overall performance. So that is a quick overview of the architecture and the components. So each piece is designed to work together seamlessly, ensuring we get the best results possible. Now let's discuss about the data sets for the stage one. That's the stage one, as I mentioned, it is a understanding training, right? That is a first phase of the training. So during this phase, so they have considered substantial amount of data pulling from 558K image text space from LCS, that is a LAYAN, CC, conceptual captions, and SVU. These space were complemented by the blip captions, which were sourced from CC3N dataset and filtered accordingly to the method outlined by Liu et al. Moving on to video text space. So they have considered 702K pairs derived from Valley dataset utilizing the WebVid dataset. This extensive collection really helps in enhancing the model's ability to understand video content alongside text. But now let's discuss what are the data sets they have considered during the instruction tuning phase. For the image text component, they have utilized 665K image text instruction sourced from the Lava v1.5. Additionally, they have incorporated video text instruction dataset that contains 1 lakh paste from video ChatGPT. So this combination of datasets allows us to fine-tune the model effectively for a variety of visual and textual data. So let's discuss the model's training process. For images, each is resized and cropped to 224 cross 224 for consistency. For videos, sample 8 uniformly spaced frames per video, ensuring uniform pre-processing. In terms of batching, they have created a random mix of images and videos to enhance model's generalization during training. So they have 2 training phases. Stage 1, as I mentioned, so during the stage 1, 1 epoch with a batch size of 256 and using AdamW optimizer and cosine learning rate scheduler to adapt the learning rate. Stage 2, the batch size is reduced to 128 for better training dynamics. And they also stored the initial learning rate with 1e power minus 3 and the 0.3 warm-up ratio. So for more details about hyperparameters, right? Actually, there is a nice appendix is attached with this paper that is nice to read. Please do have a look. Now, let's get into the quantitative evaluation. Looking at table 2, so Video Lava shines in 8 out of 9 image understanding benchmarks. So securing a top performance overall and ranked second in the one benchmark where it didn't take first. So when evaluating image understanding with 5 academic question answering benchmarks, Video Lava outperforms the leading model. That is the Instruct Blip 70 across all measures. Okay. So in summary, like more or less on image question answering as well as the benchmark toolkit things, right? So this seems to be Video Lava seems to outperform all the benchmarks against the competing methods except the one where it stands second. So basically, what we can conclude out of this slide, right? So Video Lava demonstrates a robust understanding of scene semantics. So effectively answering complex questions about images, which underscores its capabilities. So similarly, in order to test its video reasoning abilities, right? They have tested on the 4 data sets. So they have it confirms that basically Video Lava's effectiveness in understanding videos and providing contextually relevant responses. So highlighting its advancements in video question answering capabilities. So yeah, now in order to see how well it performs on hallucinations, so they have tested. It's like they have tested Video Lava. So on a Pope benchmark. So it's like in conclusion, what we can see from this slide, right? So Video Lava's success in detecting object hallucinations strongly validates the alignment between unified visual representations and the textual descriptions, which is vital for understanding the interaction between the visual and textual modalities. So in a way, if I want to summarize, right, simply the unified visual representations are helping to improve the performance on hallucinations. So again, here certain visual results, how it is performing with respect to image understanding and video understanding. So if you see an image understanding, right? So the comparison is between the Video Lava and GPT-4. So here, just I want to highlight the first 2 images, right? We are looking at this one, these 2 images, right? Which are the responses generated by the GPT-4. This is the response generated for this image, and this is the response generated for this image. This is the Video Lava response. So as we can see that it's like Video Lava come across as a more comprehensive and intuitive and logical response than that of GPT-4. For instance, in the first image, right? So the Video Lava showcases some impressive capability. It's able to predict what is about to happen in the scene, which is a quite sophisticated feature. It also identifies specific colors, pointing out that the globe is red and the ball is blue. This attention to detail really stands out, especially because GPT-4 fails to recognize these specifics. Now shifting gate to video understanding, right? The right side image. So here also, yeah, we can see one thing, that is, when compared to sentences generated by the Video Lava and the Video Chat GPT. So this is a Video Chat GPT. This is a Video Lava, first ones for everything. So that Video Lava part its ability to extract key information from the videos based on the instructions provided. So it's able to extract that key information, right? So we can see this clearly in the highlighted purple text. So there is a read book while wearing glasses. It is more detailed and attention to detail. So overall, it is fascinating to see how Video Lava demonstrates superior capabilities in both images and video understanding compared to GPT-4. And here is actually, this slide is having a very interesting thing here. So if you look at this figure, right, there are two things. See, this really highlight how well the model can handle multimodal inputs thanks to its LLM backend. Okay, this isn't just a technical detail, but it is a solid proof that Video Lava has a robust understanding of different type of media as well. For example, if you look at this one, right, this is the image. So what are the instruments in the picture used in this video? So it is able, yes, the instruments in the images are used in this video. That means it is able to understand the type of modalities as well. So, and similarly the second as well as, so as the flag is visible in the video, so it is able to understand what is the input source it is. So these results are really affirm this point. We can see that Video Lava has successfully learned to interpret both images and videos. Now let's have a look at ablation results. That means what are the learnings from this paper? Okay. So the focus on this study basically, right, when it comes to ablations, is about evaluating how large language models perform when working with a different type of visual representations. To break it down, we are looking at two specific type of representation. The first is unified representation, which utilizes language-bound image encoder. The second is separated representation that employs the MAE encoder, a well-known image feature extractor. Now, it's important to note that while we are replacing image encoder with MAE encoder, we are keeping the language-bound video encoder intact. So this setup allows us to maintain consistency in our approach. So we then conducted performance comparison between these two representations. The comparison was thorough, spanning across 13 different benchmarks. So of those benchmarks, 9 are focused on image understanding, while the remaining 4 are centered about video understanding. So this gives us like a comprehensive view of how each representation performs across various visual tasks. So like you can see here is something is interesting. So here there are two things, right? There are the performance benchmarks when we use separate encodings as well along with the united ones. That is, the unified visual representation actually performs better than the separated one across all the benchmarks, right? As well as it also helps in reducing hallucinations as well. You can see from these various benchmarks. As well as one more interesting is it is if you look at this all these benchmarks, right? Like VisWiz, its performance is also boosted on VisWiz as well as on OCR capabilities as well. So similarly for video understanding, so that is by switching out the image encoder with the MAE, we disrupt the unified learnings of visual representations, right, during the LLM's initial phase. So what this means is that video and image features are no longer aligned at the start. So now if you look at this figure, right, so it is clear that when you compare the separated visual representations to the unified one, the performance boosted significantly across 4 different video question answering sets. So here is one thing. So when authors use separate visual representation, not only resulted in lower accuracy in question answering, but also similar drop in answer scores as well. So what do we take away from this one? The unified visual representations actually helps the LLM dive deeper into the learning and understanding videos better. Now let's take a closer look at this section. The focus here is on validating how images and videos can complement each other during joint training, right? The key idea is that by integrating both formats, we can significantly enhance LLM's understanding. So unified visual representation plays a crucial role in this process, helping the model interpret images and videos together more effectively. This synergy has the potential to yield richer insights and improve the overall performance as well. So now when it comes to video understanding also, you can see it's like video lava star markers, right? This is only trained on the videos only when joint training with the image. So we can see that. So when we have a joint training that involves both images and video, right? The performance boost is happening, right? So that means that really highlights how joint training enhances the model's understanding of visual representations. It's a great example of the benefits of integrating multiple data types. So, okay, the conclusions about this thing, right? So, it's like what makes Video Lava unique? Basically, the key feature is innovative baseline, and introducing a language bind encoder. Another one is a joint framework. So, these are the things, okay? So, it's like these are the interesting contributions. And second, there are further, in addition to those three, right? So there is the effective visual alignment, right? So that means actually the image and video features also pre-aligned before projection. So that is also helping the large language model to interact across the different modalities. So that is nothing but a unified comprehension, that unified visual representation as well. And what are the future the directions suggested by the people? So first, although it really shines when it comes to analyzing both images and videos, its competitiveness in these areas is quite impressive. But however, there are some challenges that we need to address. One major area where Video Lava struggles is in understanding the temporal relationships and spatio-temporal localization. So that's definitely something we should keep in mind. Now, here is when it gets more interesting as well. Video Lava can actually serve as a solid baseline for expanding into other visual modalities like depth and infrared images. So there is a lot of potential there. And looking ahead, I think we should explore how to effectively incorporate timestamp embeddings. This could significantly enhance large visual language models, especially when it comes to answering questions related to temporal relationships.